So I have to do what? I have to operate it onto an omega. So I'm not writing it, okay, imagine I have written it here. So let's operate it on omega. And let's assume that omega, since y is a discrete random variable, so it's gonna, partition the entire, what do you call it, the sample space. And say omega is in some Bn. Okay? Then this conditional expectation of this is going to be equal to the conditional expectation of ax1 plus bx2 given Bn. Okay? And you can see very easily that this is linear. Why this is linear? Because this is the integral of ax1 plus bx2 with respect to dp over b and everything divided by the probability of bn. So it's a linear thing actually. So I know that the integral is linear. So this must be linear. So in other words, the conditional expectation in this sense is inheriting the linearity from the linearity of the divided integral. Okay? So this is one property. The other property of this is going to get rid of this. If there a shade is coming on this, it's fine. Even in the camera, huh? I'm not writing on it because I mean, if you can see it, then obviously the camera can also see. Okay. Anyway. So, what is the next property? The next property that I'm interested in is this. I will always assume in this discussion for the properties that x is integrable, random variable, and y is discrete random variable. Okay? So the next property that I would like to prove is this, that the expectation of the expectation given y is equal to expectation. So in other words, if you compute the average of the averages, you're going to get an average actually. Okay? So if you compute the average of the conditional expectations, so here's the thing. We computed, in our example, we can compute the conditional expectation of x given by for 10p and for 0, 10 and 20 and 30. Okay? So we get some numbers actually. For example, for the first case we got 25. In the other case we'll again get 25 and so on and so forth. And you take the number of these outputs that you got. If you take the average of these outputs that you got, you're going to see that this would be same as the conditional expectation of the entire x actually. So you can easily prove it. So help me out. What should I do? What should I begin?
Condition. What we find input is nothing given thereby. The condition I want to definitely.
Alright, so
I can
I
compute.
here's the thing. Let's take the conditional expectation of x given y, okay, of this actually. So it would be
Expectation of the integral.
Summation I1
Expectation of the integral.
expectation of the. By the way, if y is discrete, what would be the nature of the conditional expectation? So it will also be discrete actually. Isn't it? So we see that this guy takes different values on different events corresponding to the values of y actually. Okay? So how can I write? So this would be the summation, okay, of I equal to 1 to infinity of
Expectation of
given that
x given that y is on y.
expectation of x given y equal to yi multiplied by probability of y being equal to yi. Okay, so you get this. And now, what would be this guy actually? So I have a definition for this. So this is equal to I equal to 1 to infinity. So this is the integral, or I can, in simple language, I can write this is the expectation of x given x multiplied by the indicator function of y equal to yi divided by the probability of y equal to yi and multiplied by the probability of y equal to yi, and these two guys are going to get rid of x, and this is what is the expectation of x by definition actually. So what did you get finally? So this is the expectation of x. Are we happy that this is expectation of x, x multiplied by the indicator function?
Yes.
Because every omega is going to be in one of such.
G sir.
Yes. Or you can say that that's an integral. Okay, I can see that that's an integral of x over yi, and I'm taking, I can see in this manner. So I can say over the integral y equal to yi, and I'm integrating x with respect to dp, and then I'm taking the sum I equal to 1 to infinity. Okay, and then I can say that okay, this is equal to the integrating x over the union of all these actually, because these are disjoint, and combine them, you're going to get an omega, and hence you get expectation of x axis. Okay, so it's a interesting thing to work on. So what does this property is telling us? This property is telling us that if you compute the average of the values taken by the conditional expectation, you're going to get the average of x. Roughly average of the averages. Average actually.
वो यहाँ से follow करेगा. Y को omega function.
Y is omega. Like I said actually, y is a discrete random variable. So here is another
But beta is
property. Okay, here's another property written in the part of in the form of a proposition, which says that if x is integrable and y is discrete, then it's interesting thing. Conditional expectation of x given y is sigma of x measurable. So in other words, it's measurable with respect to sigma field generated, not x but y actually. Sigma field generated by y. So that's one of them. Second property is that if you take any measurable set from the sigma field generated by y, you will see that the integral, okay, of the conditional x given y with respect to dp over this a is equal to the integral of, I don't know why the heck we proved this, it just follows from here actually. Anyway, so a over x dp. Think about it. So why we took hassle of proving all that? We could have done it directly. So if this is true, think about it. Just take a equal to omega, and this follows. Isn't it? Just take a equal to omega and this follows. Anyway, it's like we proved, an observation and we are generalizing it. Wasted a lot of time. Alright, so let's prove these both properties. And these two properties are very important. By the way, another way to write this identity, what would be the other way to write this identity in terms of expectation? So I can also write this as expectation of x given y multiplied by the indicator function of a is equal to expectation of x multiplied by the indicator function of a. This is another way to write it. Anyway, let's prove the first property. So what this is telling you that every conditional expectation of an integral random variable with respect to discrete random variable is always measurable, with respect to the sigma field generated by that random variable, and what? And if A is a measurable set, then the integral of the conditional expectation and the random variable over this A must agree. So it must agree. So the integral of the conditional expectation and the x itself must agree on here. Okay? This means B. The one is very simple. Why it is simple? Think about it. Why this is, the first one is very simple. So here's the thing. If y is taking these values, y1, y2, so on and so forth. Okay? By the way, what is the meaning of the sigma field generated by the random variable? So by sigma field generated by a random variable, I mean it's a sigma field generated by the inverse images of the Borel sets under y-axis. Okay? That's what is the definition of sigma field. So if this is the case, what would be y equal to y1? What we can say about these? So let this is the case. Then what can I say about these guys? Y equal to y1 and y equal to y2 and so on and so forth. They all must belong to sigma of y actually. Okay? Because this is the inverse image of a singleton Borel set. Because singleton is also a Borel set. So all these belong to by definition in sigma field generated by y. And once you have it, then we have this. Looking for first part. So if this is the case, what was the first thing that you like to do? Expectation of x, y is sigma. Okay, so and let assume that expectation of x given y equal to yi, the same notation is equal to ei. So these are the values that it takes actually. Okay. Now why this guy is measurable with respect to sigma of y? Because think about it. So if I give this guy a name Z, and I consider the Z inverse of what? EI. So what would be the Z inverse of EI? So in other words, the collection of the omegas for which you get value EI. So this is equal to y equal to yi, and this is already in sigma y. So we are done. Okay. So measurability is not an issue. Let's think about the second part. Why the second part is true. Okay. Let's take A from sigma of y. From sigma of y. Okay? What we can we say something interesting about A? So see, this is generated by such kind of sets actually. This kind of sets. Sigma field is generated by such kind of sets. So if you take any A from sigma field generated by Y, then A can be written as a countable union of these actually. So I don't know which sets are going to come, but I can take some countable subcollection of this, and I can union it. That is going to give me what do you call A actually. Okay. Then A can be written as the union of maybe k equal to 1 to infinity, y equal to yik. So I don't know what these ik's are. So the ik can be 1 and 2 and 3, so it could be. So it's just could be entire, all of these. So obviously if it is entire, then this is omega, but it could be the part of it actually. Okay? And now I'm saying that consider the integral of this conditional expectation x given y over this A with respect to dt. So it is going to be equal to the integral of the union, and since all these are disjoint, so it is going to be the sum of I equal to 1 to infinity, k equal to 1 to infinity, an integral of y equal to yik, okay, of the conditional expectation of x given what? X given y, x given y with respect to dt, right? Is it making sense? Now, on each such event, this guy is fixed actually. It's a one number. It's a one number. So if I wish, I can pull it out of integral actually. Okay? I can pull it out of integral. So why this is a fixed number? Because I know that on each such subset. So in other words, you take any omega from this event, and operate this onto that omega, you're gonna get a fixed number, some constant c. Okay? So you're gonna say that this is equal to, or maybe I can assume, okay, let's just assume that you are mature enough. Okay. And I can take this conditional expectation of x given y. Okay. By the way, okay. Can I say that this would be equal to, here's the sum k equal to 1 to infinity. I would say that this is equal to the conditional expectation of x given y equal to yik, okay, and its integral over y equal to yik with respect to dp. So this guy is concretely going to take this value onto this, and that's a fixed number. It's like some eik, so it's a fixed number. So I can take it out of integral. So what I'm going to get k equal to 1 to infinity. So the conditional expectation of x given y equal to yik and what? Multiplied by the probability of this event. You can think about it. So if this guy is out, so you're going to have a 1 here. So you'll have an integral of this event with respect to the probability measure. So this would be equal to the probability of y equal to yi. Okay? And how can I compute this? So in order to compute this, k equal to, so it's just a repetition of this previous argument actually. So this would be equal to integral of y equal to yi of x with respect to dp and everything divided by the probability of y equal to yi, multiplied by the probability of y equals to yi. Okay? So just applying the definition. So this is going to get rid of this guy. Okay? And now I can write this as, so I have the integral of x with respect to dp or this. So if I can union them all, this would be same as the integral of